Got it.
All right, whenever you're ready.
Hi, everyone. Good afternoon. My name is Harrison Gu, and my partner is Jojo DeLeon. Thank you all for taking the time out of your day to hear our initial findings about accidents in the Chicago area. So, the city of Chicago has been experiencing a lot more accidents lately, and with limited funds for ambulance services, the city has hired us to predict which conditions are more likely to lead to accidents that involve an injury, so they can more efficiently deploy their ambulances. So our project objective is to investigate factors of incidents of or accidents in Chicago and determine which features are more likely to lead to accidents that have an injury. A little overview about our data. The data that we used was from the City of Chicago's data portal. And we used two data sets. One was about the vehicles that were involved in accidents, and the other one was about the people who were involved in accidents. And both data sets had crash ID. So that's how we were able to join the two data sets into one. And it started with over 1.6 million accidents, but we narrowed it down to about 162,000 rows that had all the information that we were looking for. And we also narrowed it down to 17 unique features. Links below for the two data sets that we used. So a little bit on understanding the problem and how we approached it. The first step was to identify features that we thought were going to be relevant to injury and accidents, and then get rid of all the other columns that we didn't think were necessary. And then we ran through various models, just various vanilla models to get a baseline for each model. And then for our last step, we picked two of the models that we thought performed the best for the baseline. And then we dove a little bit deeper to tune up the parameters for each one.
Originally, the combined data sets had over 78 feature columns. We narrowed them down to 17 pertinent features. Upon examination, a few seemed exceptionally notable. For instance, the vast majority of accidents occur at a street intersection. Additionally, drivers in their 20s, 30s, and 40s account for more than half of the accidents under scrutiny, with 20-somethings being the most likely of the group to be in an accident. These accident features have been juxtaposed as to whether or not an injury was sustained in the accident. These graphs show that accidents are more likely to occur during rush hour traffic, on high volume streets, and that the driver is more likely to be male. In all three instances, the rate of injury is much higher than with other features under inspection. This graph denotes feature importance of the top 12 features for our predictive model. From our baseline modeling, the most important factor as to whether an accident will involve an injury is the physical condition of the driver. Notably, the classification other for the physical condition of the driver is separate from the driver being impaired by drugs or alcohol. And although during the exploratory data analysis, we observed that the majority of drivers involved in accidents were in the age range of 20 to 49, our baseline modeling noted that having a driver of 80 years or older more significantly influenced whether the accident resulted in an injury. Furthermore, both rush hour driving and off-peak driving look to have a similar influence as to whether an injury is sustained. And although male drivers have a higher accident rate compared to females, female drivers appear to be more likely to be involved in an accident involving injuries. And not surprisingly, if a driver or passengers in vehicles involved in an accident are not utilizing safety equipment, injuries are more apt to occur.
So for our next step, we realized in all of our baseline models that they were making a lot of type 2 errors. In this context, a type 2 error would be when somebody in the vehicle is injured, but we classify them as not injured. And this has an effect on our user base because some people who are injured and need help are not going to get the ambulance that they need. So to address this, we're going to try methods such as SMOTE when we're training our data. We think that because there's a huge class imbalance in the training data. The model is more, it's better at predicting no injuries, but it's not so good at identifying the injuries. So we think that taking this approach might help their ability to reduce type 2 errors. Thank you again for your time and attention. We look forward to our next meeting where we will be presenting our final findings about accidents and injury relationships. And if you have any further questions, the project repo is linked below, as well as the contact for Jojo and myself.
Thank you.
Thank you.
Awesome. Thank you, Jojo and Harrison. So Justin got here, but I'm going to give you like a couple of minutes, Justin. So we'll move on to the next person, and then Dimitri and Justin, you'll go next. So next up, we'll have Justin Wabel.
Let's see. Okay, let's start. Let's do. Okay, let's get this set up. Okay, which screen can you guys see?
I see your presentation.
You see the presentation, not the other one. Okay, let's see if I. Okay, then let's see if I do that. Do you see the presentation still?
Mm-hmm.
Okay.
Oh, and
Good.
wait, I see like a side thing.
Yes. Okay. I was worried about that. Okay. All right. Then I will do this. Okay. All right. All right. Thank you for your time. I was tasked with looking at customer churn analysis based on for Seriatel, the business case. The idea is that we are looking to see what causes customers to churn and switch off of the service. If there are different factors that customers are looking for and what features. So the data that I analyzed came from 3,333 customers, and it included information on all sorts of things, including account length, international plan, whether they had a voicemail plan, numbers of voicemail messages, customer service calls, and all of the various charges, call lengths, and things that customers might find. Out of that total of 3,333 customers, 2,850 customers were retained and 483 churned. So we have a 14% churn rate. So for my modeling purposes, I wanted to look at what is at predicting the churn, whether they actually churn or not. Didn't matter, because if they are predicted, if the model predicts them to churn and they don't churn, great, we didn't lose a customer. I just wanted to make sure that it was able to predict with 100% accuracy that we got that if someone was going to churn, that they would churn, and that we wouldn't get any problems with that, and we wouldn't predict that someone would churn and then would not churn, and then they ended up doing so. So here's the classification model that I used. The model that I used has a precision score of 0.97 when predicting retention of customers. It has a precision score of 1.0 when predicting somebody who's churned. Now, there's an error of a recall. As you see, the recall score of 0.83, there's an error of 17%. So 17% of the people that we predict, that the model predicts will churn, end up not churning, but that's not a big problem, because I would rather, based on my model and my analysis, I would rather predict that someone would leave and then they decide not to leave, rather than predict that they're not going to leave and then have to deal with them actually leaving. So the top factors that I found affecting churn, I used the model as a starting point for data exploration as to what might be causing churn. And the features that I noted were the total charges, the voicemail plan, the customer service calls, and the international plan that was on offer. The total charges were interesting because customers who pay more for their service tend to churn at a higher rate. This is also subject to differences in time of day, because we do have charges for day, evening, night, and international. And customers who churn, who pay higher day charges, also tend to churn more frequently than those who pay lower day charges. Overall, customers who churn pay $65.35 on average for their service. Customers who don't churn pay $58.45 on average. As far as the voicemail plan, voicemail is also interesting because only 28% of the people who subscribe to our service have a voicemail plan. So it's a very interesting kind of setup. The 83% of the customers that churn don't have the voicemail plan, and 17% of the customers that churn do have it. So there's some sort of disconnect between how we're looking at the voicemail, which we'll get into in the recommendations. Customer service calls also were interesting because 79% of the customers who've churned make at least one call to customer service, and over half of the customers that churn have made 3 or more calls to the customer service line. So that may need to be something that needs to be addressed. International plan is also interesting because only 10% of our subscriber base actually subscribe to the international plan. And when looking at the charge per minute of the international plan, there's virtually no difference in cost per minute between those who have an international plan and those who don't. On average, those without an international plan making international calls are being charged 26.8 cents per minute, where those with an international plan are being charged 27 cents per minute. So it's pretty much indistinguishable. So that leads to the recommendations. The first recommendation is to evaluate the rates we're charging our customers. It seems that based on the high churn rate of people with high charges, we may be overcharging our customers, and they may be looking at other areas. That might be something to investigate as to what our competitors are doing, to find ways to maybe giving incentives to bring rates down. But for one reason or another, the higher rate of charge, the higher rate that they're being charged, the more they tend to churn. The second recommendation is to give more advertisement to our voicemail plan, because given the lower number of subscribers to the voicemail plan, it seems that people are either unaware that it exists or they don't really care one way or another. So we might need to look into that in terms of getting more interaction with that plan, and in terms of marketing and so forth. We'd also like to evaluate customer service and what we might be able to do to assist the customer. It's not great when customers have to make 3 or more calls and then immediately turn off the service. Half of them are doing that. So that's not a good thing. Also, given the number of customers that churn after just one call, that also could be tied in with cost. People calling customer service lines to complain about the cost of their service and seeing what we might be able to do to reduce their cost, and then being dissatisfied and immediately canceling their service. We also might need to look into our tech support as to whether we're giving good customer service, whether they're satisfied with their calls, whether we're providing them with the correct solutions, or if they're just unhappy with the quality of this customer service and decide they're no longer going to be doing business with us. The last recommendation is to research whether or not an international plan is actually worth spending money to provide. And if it is, look at ways that the service might be improved. Since very few customers are actually subscribed to it, and the cost between having an international plan and not having an international plan is pretty much negligible if you're making international calls, there either needs to be an incentive given for those who do have an international plan to keep them on our service, or we need to look into whether we really even need an international plan at all if the overall cost per minute tends to be the same whether you have one or not. Thank you for your time. Those are the recommendations. As you see, there's my contact information, and have a good afternoon.
Awesome. Thanks, Justin. All right. Next up, we'll have Dimitri and other Justin.
All right, thank you. Let me share my screen. All right. Everything good?
Yep, whenever you're ready.
Justin, you ready?
Indeed.
All right, here we go. Hi, everybody. My name's Dimitri Belazerski, and I'm here with my partner, Justin Hugh, and we'd like to welcome the representatives from Potabilities to our first team update. Potabilities, as we all know, is a hot new startup manufacturing a groundbreaking device that will be able to quickly test the potability of water anywhere in the world. While your engineers at Potability are hard at work on the physical device itself, we are working on the back end to create a model that can quickly determine the potability of any water sample based on the prevalence of key features.
All right. So there are 9 essential features in determining water quality, according to the World Health Organization and the U.S. Environmental Protection Agency. Our data includes samples from 3,276 different water sources, but even with such a large quantity of data, unfortunately, it's not as pristine as we'd like. Some values are missing from the key features, so we employed some various methods to combat that missing information.
In the course of our EDA, we evaluated the data we had and noticed that almost 2/3 of our data was for non-potable water. To make sure that our models were performing at peak efficiency, we created a scatter plot of all of our data to see the separability of our target. As you can see from this graph, the long orange dashes is our potable and non-potable data, and it is incredibly easily separable, meaning that we do not have to do any further data manipulation, such as smoothing, in order to balance out our target class.
Right. After running our models, we concluded that these features here are the most important and influential for determining water potability. So those include pH, hardness, sulfate, chloramines, and solids.
After running dozens of tests on 9 different models with various conditions, we settled on these top 3 performing models: the bagging classifier, the random forest classifier, and the gradient boosting classifier, which all performed above a 65% accuracy in our testing results. They all happen to be tree models.
Okay. So our best performing model turned out to be grid search of a bagging classifier, and we dropped all of the null values that we talked about earlier that were missing from some key features. So the training data, as you can see there, trained perfectly, which is a sign of overfitting, but it was overall still our best model so far, with 70% accuracy on the test data. And this is our final model report. So there you can see the precision for the train. The model precision for non-potable water is slightly higher than for potable water, but we're actually encouraged by that, since we would absolutely prefer to lean on the side of caution with our life and death recommendations. We would rather call clean water dirty than the other way around.
In continuing to improve our model, we will require further testing by manipulating our grid search parameters. We would also like to try some other methods of filling in our missing values, for example, with the standard average or other things that we can possibly play with. The most surefire way of improving our model will be through the collection of new complete data, which means that the device that Potabilities is currently building will actually become better and more accurate as it's used on more and more new water samples. As more data becomes available, we would like to see if splitting the data by region can have an effect on the performance of our model as well. Thank you for our time, and we look forward to our next meeting when we can update you on our new progress and findings.
Awesome. Thanks, Dimitri and Justin. All right, next we have Katarina.
Okay, let me share my screen. Okay, welcome everyone. My name is Katarina Salcedo, and I will be presenting a classification model that can be used to predict functionality of water wells in Tanzania. So motivation behind this, Tanzania is currently in a water crisis, which means that there is not enough fresh water resources to meet the region's demand. Around a third of the country is arid to semi-arid, meaning that it has little to no rainfall. And unless you're surrounded or near one of these 3 lakes, you have to rely on groundwater and surface water, which is easily contaminated from bad drainage systems, bacteria, and human waste. Because of this, waterborne illnesses account for over half of the diseases that affect the nation. And on top of this, walking 3 to 5 miles to get water puts your safety at risk and also your education. So they get trapped in this cycle of, poverty and whatnot. Okay. Oh no. Okay. So the goal behind this is to provide the water project with information on the status of wells. This can help them decide where to build next, what type of wells they should build, and help determine which wells need maintenance. To look at this, I sourced data from Tarifa and the Tanzanian Ministry of Water. It contained around 59,000 rows and 40 independent variables with information on geographical location, funder, management, population around the well, quality and quantity of the water, how the water is extracted, the source, and if payment was required. Our target variables were whether the well was functional, non-functional, or if it needed repair. Some EDA, I looked at the separability of our independent variables. So the top graph is an example of data that's not very well separated, which is important to our classification model to be able to determine, make these distinctions. So columns that showed low separability, like the top, were dropped from our data, and the bottom is an example of something that showed good separability. So those were the columns that we kept. Something else we dropped were redundant columns. So you can see that the graph shows extraction type class. There was also extraction type group that was dropped. There was payment type and payment, quantity and quantity group. So those were dropped. We ended up with 16 independent variables. There was also some null values in our data that we ended up dropping. So we were left with around 50,000 rows, which is still, a lot of data. Something else that I found was there was class imbalance in our data. So most of our data was on functioning wells, and only 7% was on wells that needed repair. I didn't do anything about this right away. I wanted to see how our initial model was predicting how it was doing. This is our initial model. I decided on a random forest classifier after running a few other vanilla models. This one performed the best. There's a lot of information here. What we're interested in is the accuracy scores, which is 83% for the training and 78% for the testing data, which is both pretty good. And since they're pretty close together, we say that our model is not overfitting to the training data, which is a good sign. Something else to look at is the F1 scores. It's basically a combination of precision and recall. And we can say that if the F1 score is high, then our model is doing pretty well. So we see that for functional and non-functional columns, our model is doing pretty good. But for that second one, the functional needs repair, it's not doing very well because there's only 7%. So in our final model, I ended up removing that column, and it improved our model's accuracy to 88% and 84%, which is pretty good. The F1 score is also increased. Looking at the confusion matrix, we see that for both the train and the test, our model is over predicting functional wells. So, which can be also due to the class imbalance, because I think it was 60-40%. So maybe fixing that would help it out a little bit. So something to tweak in our next steps. But overall, our model is able to predict with 84% accuracy the functionality of wells. The most important features were quantity, whether the well was dry or insufficient or enough, the water point type, which is like if it's a communal standpipe, a hand pump or a spring, the extraction type, and if payment was required. So next steps would be to improve the accuracy from try to go above the 84%. Maybe do some more feature engineering, like getting the age of the well, and also plotting locations of functional wells to see which areas might be in greater need. Thank you.
Thanks, Katarina. All right, next we have Naomi.
Hi. Let me share my screen. And
Awesome, we see it now.
hello, I'm here today to update you on our progress with our travel insurance prediction estimates. As you know, you contracted our firm to project which customers will be more likely to buy travel insurance based on previous activity. With this information, you hope to target these individuals first and spend more of your resources on them. So some information about the data that you provided us with. This data was sourced in 2019 when you offered 2,000 of your previous customers the option to buy a new package. It took into account a number of features, including age, employment type, graduate or not, annual income, number of family members, whether or not the person has a chronic disease, whether or not they're a frequent flyer, and whether or not they traveled abroad. Some of the EDA that we did on this data, in order to prepare the data for modeling, we standardized the data, making sure it was on the same scale, encoded the categorical data so that it could fit through the model. And since there was a significant class imbalance between those who bought and those who didn't, we had a 65-35 split, favoring those not buying. We ended up using SMOTE to synthetically engineer some data in order to balance this out and get better predicted results. We also analyzed various features to get a sense of how the data was distributed. Through this process, we're able to see that while overall more people chose not to purchase the travel insurance, there were 4 groups of people who tended to purchase. Those with incomes over 1,350,000 Indian rupees, which is equivalent to 18,000 USD. Those who are frequent flyers, those that travel abroad, and those that are over 33. You can see in the graphs over here, the orange section represents the people that did, or the groups of people that tended to buy travel insurance more. So frequent flyers over here, those that traveled abroad. On the previous slide, we had those over 33 and those with a higher income. Our modeling process, we ran a number of base models with default parameters to form a starting point. As you can see, from the classification report, the base model has a 0.73 precision, 0.93 recall, 0.82 F1 score, and 0.73 accuracy. While these are not bad, there's definitely room for improvement. So after we looked at the base model, we used grid search model in order to find the best hyperparameters for this data set. After that, we went back to the base model and to see how SMOTE would improve those results. And then finally, we used the grid search and SMOTE together in order to get our best and final model. Our final model was a XGBoost model utilizing the grid search and SMOTE. We got a precision of 80, a recall of 91, F1 score of 85, and accuracy of 8%. The features that the metrics that we are most interested on here are accuracy and F1 score. And you can see that there is a significant improvement on both of these ends from our initial model to our final model. For our next steps, we would like to target those that are in the 4 classes of people that tended to buy travel insurance. So again, those that are frequent flyers, those over 33, those that travel abroad, and those with income over 1,250,000 rupees. It was also interesting to note that in the data that was provided to us, the highest age was 35. So we want to see if we can find some older people, because it seems to be that the older you get, the more likely you are to buy travel insurance. We'd also like to create a survey to determine why customers do not choose to renew their policies. Because again, all of the people that data was gathered that had been customers at one point. So if they did not choose to continue, we'd like to know why they did not. And hopefully that would help us in understanding some things that we might need to fix. And we would also like to analyze submitted claims versus claims covered to be more transparent with our customers and to gain their trust. For more further information, feel free to email me. My email's over there. And to have a look at these machines yourself, you can take a look at my GitHub repository. Thank you so much for your time.
Awesome. Thank you, Naomi. Next, we have Noel.
Okay, there you go. Can you see that?
Yep.
Yep.
Okay, great. Good afternoon, ladies and gentlemen of the City Council. My name is Noel Ferrari, and I am presenting my investigation into bias in the SPD. As you know, the Seattle Police Department has been under extreme public scrutiny in the last year in the wake of 2020's Black Lives Matter protests, particularly the Capitol Hill Occupied protests. And you are considering budget cuts due to increased public pressure for reform, including some calls to abolish the police entirely. So in order to provide sort of a balanced look at this issue, I'm looking at Terry stop data, which has been made publicly available by the city. Terry stops have been critiqued as contributing to over-policing in low-income communities and communities of color, providing legitimacy to racially biased systems and perpetuating systemic injustice. That said, I know that this is a kind of a sensitive issue, and so it's very important when taking action not to rely only on emotional arguments, but to look at the data and see what it tells us. So that said, we'll look at Terry stops by the numbers. And just to start right off, comparing racial demographics, you can see the blue bar on the left is the population of Terry stop subjects, and the red bar on the right is the population of the city of Seattle. And so this right off the bat, before we do any predictive modeling, shows us that there is a bias in who is being stopped. White subjects who make up 67% of the population of the city are only subjects of about 50% of stops, whereas Black subjects make up only about 7% of the population, but they are subject of almost 30% of police stops. The second thing I wanted to look at was the impact of the Black Lives Matter protests in the summer of 2020 on police activity. So I want to ask the question, when the police know that the public is looking at them closely, does that impact their behavior? So I started by looking at Terry stops in 2019 to kind of establish a baseline. And when we look at 2020, what we see is that there is a huge decline in the summer of 2020. The Black Lives Matter protests began on May 30th. The Capitol Hill Occupied protest lasted from June 8th to July 1st. So you can see there's such a sharp drop off in June that indicates that, yes, officers do behave differently when people are watching. I want to mention also just this associated spike in no action stops that correlates with extreme shelter in place orders due to the COVID-19 pandemic. there's a spike in these no contact stops in the spring during the first shelter in place order. And you see it again crop up in the fall during the second fall shelter in place order. So I believe that has an impact on this data also. So taking a look at some predictive modeling, because our data set has features like whether or not the subject showed ID to the officer, whether or not the subject had whether a weapon was found on the subject during the stop. These models are not intended to be used in the field to help officers predict who to stop. And I don't think there's a model that could be created to do that well. But predictive modeling can tell us what features of a stop are most important in determining the outcome, which can show us if race or other factors are playing an impact or do have an impact once the subject has already been stopped. So my first model, you can see that it performs okay with about the best accuracy is about 64%. And I'm using accuracy kind of as my main scoring metric because I want to see how well classes are being predicted. But you can see that taking sort of a wider look at our the class breakdowns in our SVM model, which is the best model in this iteration, that arrests in particular are being very poorly predicted. There's not a strong difference between stops that result in a citation versus stops that result in an arrest. So to combat this, I condensed arrest and citation into one category and built my second model to predict whether or not a stop resulted in police action. And you can see that this greatly increases the accuracy of the model across several different models. By tuning an XGBoost model with grid search, we're able to predict whether a stop results in further police action with 84% accuracy, which tells us that there is something that these stops have in common. Looking at what's most important in predicting whether a stop results in police action, we can see far and away this call type, no call, and subject ID, which is whether or not the subject provided identification to the officer when asked, are the most important features. These no call, which means the officer saw something and stopped someone based on what they saw, overwhelmingly do not result in police action, whereas stops that come from a 911 call overwhelmingly result in police action. But what we see here when we break down these call types by the race of the subject is that there isn't the distribution of the subject race in each of these groups is fairly similar, which to me indicates that once a stop has been made, the subject's race is not particularly useful in determining whether or not action will take place. And that sort of bared out to just looking at the feature importances rate. Unknown is up there, but it's a very low importance. So my conclusions and next steps is that there is some racial bias evident in the data. Black subjects are much more likely to be stopped, but once a stop has been made, race does not play a large factor in whether or not action is taken. But stops made without an associated 911 call are much less likely to result in police action. And so efforts should be made to reduce those types of stops. However, large scale data collection issues made stronger conclusions difficult to draw. And additional data about arrest outcomes would add depth to our analysis. For example, whether or not a weapon was found is the only metric that we really have that in this data set that shows what might happen. There's no information about like if drugs are found or anything else like that. And there's no there's no data about what happens after an arrest or citation is made, if that arrest results in prosecution. So that makes some conclusions also more limited. Thank you.
Awesome. Thanks, Noelle. Next, we have Taylor.
Hey, y'all. Let me get my screen share going here. Thanks for your patience. All right, so thank you for your presence this afternoon. I'm here to talk about the customer retention rates in a report pulled from the SiriaTel CRM system. And the purpose of this analysis is to dig into how SiriaTel might address the customer retention rates. So the organization of this today is first, the purpose of this analysis is, again, to talk about the customer churn rate for SiriaTel customers, which is currently 15% or 14%, I'm sorry, within the given data set, and customer account lengths range from 1 to 243 days with a mean day length of 101 days. After some exploratory data work, I moved on to develop some initial models during which I corrected for class imbalance, which was given by the fact that only 14% of these customers are churning. So there were a lot more customers not with longer service than not. I also applied some standard or Z-score scaling. And so after we go through the methods, then I used classification methods for this analysis. And so after I took a look at about 10 different types of classification models, and from there I chose to move forward with the development of an XGBoost model as it provided the best overall performance. And then we'll move into some suggestions about how SiriaTel might move forward from there. First, a little bit about this data. There were 3,300 customer records, which to me struck me as a very small number of records. That number of records barely qualifies as a census recognizable small town, and most people have many people have cell phones. This data was representative of 51. It was data from United States customers, and 51 states were represented, yet there were this limited number of records. So I suspect that this data set is hardly representative. And the data was a mix of categorical and continuous data types. There was also a fair amount of redundancy in this data. So for example, there were columns regarding minutes used and charges accrued, which are directly associated by the rate that the customer is charged. So there was some noise that I addressed in the data before moving on to modeling. And digging into the features of this data set, which included information regarding the customer account configuration. So do they have a voicemail plan? Do they have an international plan? What types of minutes do they use, day, evening, night? That sort of information. There was no demographic information regarding the customers, which I think could be helpful to an analysis. But within the features of this data set, I actually found that many of the qualities of these accounts were normally distributed. So I was initially concerned about the separability of the data. Despite the distribution of who had which services, so like many more people did not have a voicemail plan than had a voicemail plan, but within those categories, the churn rate was pretty normally distributed. So that was why I was initially concerned. And there were a handful of things that I noticed off the bat, which is New Jersey has a particularly high percentage of customers churning. An increase in calls to the customer service line was correlated with an increased churn rate, reduced retention. And like I said before, some of the features collinear and were causing some noise in the data. So I cleaned up things that needed to be cleaned up and moved on to modeling, and hoped that viewing some of the feature importances of the models would provide a little more insight into where this classification and separability in the data would be happening. So using a function, I applied 10 vanilla classification models and wrote the output to this data frame. From this information, I noticed immediately that the XGBoost was performing well across both the training and the test set. It performed perfectly on the training set, and then very consistently across accuracy, precision, and recall measures on the test set. So that being able to predict customer churn to between a 95 and 96% correctness would be helpful just straight out of the box. So I chose to move forward with the XGBoost model, and I worked to optimize those hyperparameters. And I also explored the random forest model, which is not particularly striking in this initial sort of run through with the default model settings. But I was able to optimize that one as well. So I ran 100 I'm sorry, Parks Main, please be quiet. I ran 100 cross-validation folds on this data set using the default model parameters because they performed well in the initial modeling, and I wanted to understand how consistently the performance would be across different train test splits. I recorded the results of the cross-validation process, and I plotted the ROC and AUC curve. So the measure of area under the curve was high, which is essentially signaling that this model does a good job of separating the signal from the noise, despite my initial concerns about lack of separability. Yeah, the AUC, if you can see in the bottom right-hand side of the screen, is nearly 1. So that probability is high. After seeing this, I went on to perform hyperparameter optimization on the XGBoost model, first using a random grid search and then a within range brute force grid search. This method changed. I did that because I wanted to sort of explore a wide range of hyperparameters initially, and then focus in on the areas that showed promise. This method changed the hyperparameters only slightly and degraded the performance. It improved, as you guys saw, the default model perfectly classified the training set, which I'm not particular, I was more interested in optimizing performance on the test. But when I changed the hyperparameters, it caused some overfitting. Stop playing with the magnetizers for a few minutes. Thanks, guys. So anyway, going through the process of tuning the hyperparameters, I found that honestly the best balance between the bias and the variance in this model was provided by the out-of-the-box XGBoost hyperparameters. Also worth noting, the average training and testing time for all of these cross-validation folds was less than 2 seconds. So I felt like the XGBoost model provides a good balance of performance and computational efficiency for if you would want to deploy this into production. So some of the limitations in this data set were, again, the number of records. I am concerned about that in terms of this model's level of predictability. And there were, excuse me, I also think that customer churn or customer retention might be better analyzed as time series data, because looking at account length in this data set as the binary measure of either churned or didn't churn is qualitative and sort of descriptive. And I think it should be more of a quantitative measure. I think a stronger target might be at what point or points in a customer's life cycle, account life cycle, are they likely to churn, and how might the company address those periods of time rather than this existing binary measure. So thank you for the time this afternoon. If you're interested in the nitty-gritty of this analysis, you can check out my GitHub repo link which is provided here, and my email address is provided. Thank you.
Awesome. Thank you, Taylor. And with that, that concludes our phase 3 project presentations. Really good job, everybody. I'm going to stop the recording here.